Welcome to today's talk. So today we have with us Dr. Yvon, and she will be speaking on finite quotients of the braid group and its generalizations, part 2. Yeah, over to you.
Right. Thanks so much for the introduction, Soumya, and thanks again for inviting me to give a talk. So today I'm going to be talking about the second half of my project with Nancy Sherrick, who's at the University of Toronto. So in particular, today we're going to be talking about finite quotients of welded and virtual braid groups. So the overview today is we're going to talk about classification theorems on the size of finite images of homomorphisms for virtual and welded braid groups. Just a quick disclaimer, I'm a topologist, but virtual and welded braid groups are really algebraic objects. So this is more my collaborator Nancy Sherrick's wheelhouse, but hopefully today I can give you guys a nice overview about virtual and welded braids and how you can use totally symmetric sets, which were originally more of a topological idea in this more algebraic sense. And so again, our main tool is going to be totally symmetric sets. And the interesting part about totally symmetric sets in virtual and welded braid groups is the totally symmetric sets themselves have some nice symmetric properties. Okay, so to get started, I want to give an overview on virtual and welded braid groups. And I want to talk about why we study them and also some nice facts about them that we'll use throughout. Okay, so why do we study braids? Well, the study of braids is highly tied to the study of knots. And a knot is the image of a continuous injection of a circle into R3. So here are some examples of knots. So on the very left, we have the unknot, then we have the trefoil, then we have the figure 8 knot. And then I think the knot on the very right doesn't have a name, but it's still one of the prime knots. And when you look at the knots, you see that you have crossings that are akin to the crossings in the braid group, where one strand is traveling over the other strand. So on the other hand, a virtual knot is a generalization of a knot where you include a virtual crossing. So what we mean by a virtual crossing is you still see that we have the same crossings that we had before, as in the braid case, but we include these extra crossings here that we mark off with a little cross. And so these crossings are different than the regular crossings, and we'll see later why they're so different. And in this talk, we're going to denote a regular braid crossing as by a sigma, and we're going to denote a virtual crossing using tau. So one of the important theorems in knot theory is Alexander's theorem. And Alexander's theorem tells us that every knot can be made as the closure of a braid. So what that means is that if you start off with a braid, you're able to do this procedure where you take the strands, the one that starts at position 3 and ends at position 3, and you're able to close it off. And similarly, the strand in the second position will get tied up to the strand in the first and also in the second position, and so on and so forth. And you're able to see this create a knot. Similarly, Alexander's theorem also holds in the case of virtual knots. So every virtual knot is able to be made as the closure of a virtual braid. So the same process here works where you take the strands that are in the same position and you connect them together. And so here we have a virtual braid closure. So this tells us why we're studying braids in order to study knots, because if every knot can come from a braid, then it's worthwhile to study braids themselves. Another important theorem in the study of knots and braids is Reidemeister's theorem. Reidemeister's theorem tells us that two diagrams will represent the same knot if and only if they can be deformed into the other by using a finite sequence of Reidemeister moves. So for the braid group, for regular knots, the Reidemeister moves are as follows. We have the R1 Reidemeister move, which is when you have a loop. So you can think about just putting a little loop into a string but then when you pull it tight, it goes back to just a straight line. So that's an R1 move. An R2 move is when you have a strand and then another strand crossing over it. You can pull them up and down past each other. That's an R2 move. And then an R3 move is when you have a crossing, but a strand living under the crossing. You can slide the crossing past this center crossing here. So here we see what appears to be a very complicated knot at the top left, but using Reitemeister's theorem, we're able to show that it's actually equal to the unknot. And so the reason you can see that it's the unknot is here we're able to use an R2 move to get from the first picture to the second picture. So we're going to use a Reitemeister 2. To get from the second picture to the third picture, we're again using an R2 move because we're pushing this and this part here up. To get from the third picture to the fourth picture, we're again using an R2 move because we're taking this little piece and pushing it up. And then to get from the fourth picture to the fifth picture, we're going to take this little piece here and loop it as an R1. And then to get from the fifth picture down to the bottom left, I believe that what we do is, oh, I don't see it, hold on. We push out this right here. So we're going to be doing an R2 there. And then to get from the bottom left to the next figure over, I believe that what we did there is we do another R2 on this piece here. Is that correct? Yes, that's correct. And then here we're doing an R2 where we push this out in that direction. And then finally, you're able to start to see it all come together. We do one last R2, and then here we do an R1. And so this finite sequence of moves shows us that something that originally looked really complicated was really just the unknot. And so if there's a finite sequence of moves, that's how you know whether two knots are the same or that they're different. So another important thing about the Reitemeister moves is the Reitemeister moves tells us why we have the presentation of the braid group that we have. So the commutivity relation, so the far commutivity relation just tells us that since two strands are far enough apart, you can do them separately. So you don't see that encoded in the Reitemeister moves, but you do see the braid relation encoded in the Reitemeister moves. So if we recall what the braid relation looks like, so here we have sigma 1, sigma 2, and sigma 1 again. And if we compare that to doing sigma 2, sigma 1, sigma 2, notice that the strand on the bottom is loose, and then the strand on the top has the crossing. So we're just using the R2 to move the strand on the bottom around, which is just the Reitemeister 3. So the Reitemeister 3 is actually what tells us that the presentation of the braid group has to include the braid relation. So similarly to regular knots in the braid group, we also have extra Reitemeister moves to encode what's happening for the virtual crossings. So for virtual knots, we have the R1, R2, and R3 Reitemeister moves. But we also include some extra virtual Reitemeister moves. So similar to the R1, we have a virtual R1, where so long as it loops itself, you can pull the loop apart. Similar to the R2, if you have two virtual crossings in the same way, you can also pull the top strand off of the bottom strand. And then here we have what looks to be similar to the R3, but with all virtual crossings. And then at the bottom right, we have a mixed relation. And very specifically, the mixed relation has one regular crossing and two virtual crossings. There are no mixed relations with only one virtual crossing and two regular crossings. And so as with the braid group, we're able to see that the Reitemeister moves encode what the presentation of the virtual braid group should be. So again, R3 will tell us that we're going to have a braid relation. The top right will tell us that each of the virtual crossings have order 2. The bottom left is called the tau braid relation. And then the bottom right is called the mixed braid relation. And so from these Reidemeister moves, we're able to see that the presentation of the virtual braid group is very similar to the regular braid group, but with quite a few more relations. So on the very left, we see that we still have the generator sigma I, which is the same braid crossing as we knew before. And then we also have the generators tau I, which we denote with a little circle around the crossings to denote that it's a virtual crossing. So as with the braid group, here we have the braid relation. And we have far commutivity. And then from one of the virtual Reidemeister moves, we have that the tau elements are order 2. And then from one of the other virtual Reidemeister moves, we have a virtual braid relation. Just like with the far commutivity of the regular strands, if the two strands are far enough apart, you're going to have that the tau elements are also going to have far commutivity. And then you also have mixed commutivity because, again, if the strands are far enough apart, they don't actually interact with each other in that way. And lastly, we have the mixed braid relation. And again, it's really important to notice that for the mixed braid relation, you have 2 tau elements and only 1 sigma. There is no mixed relation if you have 2 sigma elements and only 1 tau element. All right, so the virtual braid group and the regular braid group are pretty related because you can think about the virtual braid group as being the regular braid group, but we're tacking on something like a symmetric group. So for the braid group, something that we know is that there's a short exact sequence from the pure braid group to the braid group to the symmetric group. And the reason we have this exact sequence is you can think about a map from the braid group to the symmetric group by keeping track of a strand about where it starts and where it gets mapped to. And then the kernel of this map is what gives us the pure braid group, because by quotienting out by this map, you're getting only the braids back that start and end in the exact same position. So something interesting about this short exact sequence is this short exact sequence does not split. And the reason that we can see that it doesn't split is if it did split, then the symmetric group would have to be a subgroup of the braid group. But the braid group doesn't have any torsion, so this isn't possible. So that's one way to see why this doesn't split. So on the other hand, we have a similar exact sequence for the virtual braid group. So we have a short exact sequence from the pure virtual braid group to the virtual braid group to the symmetric group, where again, we get the pure virtual braid group by looking at the kernel of the map that keeps track of where the strands start and end at. And on the other hand, this is a sequence that does split. So the proof for this is very algebraic. I don't know a good topological or geometric reason for why this is true. And if somebody does know it, I would really love to hear it. But part of the reason why you can think that it's true is because you can see the symmetric group sitting inside of the virtual braid group, because the tau relations actually kind of encode the symmetric group inside of the virtual braid group. So here is the semi-direct product decomposition of the virtual braid group. And the next thing to think about for braid groups is we know that for the braid group, we have the short exact sequence here. So this is the Verberne exact sequence. And for those of you who are familiar with mapping class groups, you can see the Verberne exact sequence because for the braid group, you have a disk and you have end punctures. And the first map from Fn-1 to the pure braid group is called the push map, where you choose one of the points and you put your finger on it. And the map that you're doing is you're just pushing that point around the surface. And when you push that point around the surface, you see that there's a fundamental group of rank N-1 sitting inside of the disk. This is really similar to how we were able to talk about how in the last talk that Dyer and Grossman were able to reduce their problem at looking at automorphisms of the braid group to looking at automorphisms of a free group. So this is just the push map. And then the second map is when you take a pure braid and you forget about one of the strands, which is called the forget map. And something interesting about this exact sequence is that it does split. And because it splits, we have something that we call combing. So when you see the semi-direct product decomposition here, we have the pure braid group on N-1 strands, and then we have a free group on N-1 generators. And the free group on N-1 generators, that's you taking the first strand and doing all of the crossings for the first strand first. So you can think about the first strand being a fundamental group sitting inside the braid group because it has to loop around the second strand, the third strand, and the fourth strand. And then the next piece is you finishing the rest of the braid on the remaining N-1 strands. So here we see a picture of a braid, and then it's combed decomposition. So this is when you continue looking at the split sequence of the virtual braid group, because you can see this as a sequence of free groups up until you hit the last two strands. But then you see a PB2 sitting inside. But the reason you can do this is because of the Reidemeister moves, you can always push the strands around each other. And the most that you're going to do is build up some extra loops going around some of the extra strands. So here we see the red strand. And then the other strand that we have is that it's wrapping around is this blue strand right here. And so the very top, because the Reidemeister move, we're able to just push that through the bottom. And then in order to get this part of the red strand here through the top, you just have to create a little extra loop around the blue strand so that it can pass by the green. And then you can continue doing this method, which is how you get combing for the pure braid group. So on the other hand, for the virtual braid group, there is no combing. And the reason why there's no combing is because you don't have the mixed braid relation for 2 sigmas and a tau. So the relation that you would need in order to have combing is this one right here, where you have your tau, and then you have 2 sigma crossings here. But notice that if you want to be able to comb, you need to be able to pull the strand on the top down to the bottom at times. But there's no way to take the strand on the top and to pull it down to the bottom. So we can't do that, which is why there isn't any combing, because you don't allow certain strands to pass through other strands. So even though we aren't able to comb, something that we do know is that the pure virtual braid group has an incredibly nice presentation. So the pure virtual braid group is actually able to have a very different presentation than the regular braid group, the regular virtual braid group. So this is the presentation of the pure virtual braid group. The generators are fairly complicated, but you only have 2 relations that you need to worry about. So on the left here, we have the first generator. So this is the generator that we denote sigma ij when I is less than j. So here we have strand I, and here we have strand j. And what you should think about is you're taking strand j, and you're doing virtual crossings until you're past strand I. Then you're going to do a regular braid crossing with strand I, and then you'll do virtual crossings until you're back in position j. When j is less than I, so at this point you have strand j is over here, and strand I is to the right. You're going to start by doing virtual crossings until you've passed strand j minus 1. Then you'll do a regular braid crossing past strand I, And then you'll do all of the virtual crossings until you're back home in position J. So for the pure virtual braid group, you only have two relations that you have to worry about. So sigma ij and sigma kl will commute so long as I, j, k, and l are all different indices. Similarly, you have a type of braid relation where sigma ij, sigma ik, sigma jk will have the two elements on the left and the right swap, so long as I, j, and k are all different values. So something to notice is, so I'm going to denote the set where you fix the first index, but you let the second index vary over all of the values that are larger than the first index by Ri. So we denote these the right generators because they look like they're going towards the right. And we're going to notice that they satisfy the conjugation relation for the totally symmetric sets. So to remember from last time, what the conjugation relation says is that for a set to have the conjugation relation, you have to be able to send one element in the set to another element in the set using only elements of your original group. So to see this, the elements sigma ij, the way that you write them out using the elements of the virtual braid group are that they're tau I plus 1, up to tau j minus 1, sigma j minus 1, tau j minus 2, all the way down to tau I when I is less than j. So using the relations of the braid group, conjugation by tau j, sends sigma ij to sigma I j plus 1. But it will leave every other element fixed. So it's not going to fix any other, it's going to fix all of the other elements in the set Ri. And so would you guys like to see this computation, or do you want to black box it?
Yeah, is it easy to see or you have to do a lot? I mean,
it's pretty easy to see.
Okay.
It's just a couple of braid relations. So the way to see it is that
then we can see. Yeah.
Yeah. So the way to see it is if you do tau j on both sides. So if you have tau j, tau I, so far commutivity tells us that this tau j element is going to commute with all of the other tau j's so that it can go all the way next to sigma j minus 1. And then something else that we want to do is we're going to add in two other tau j elements here because we want to use the mixed braid relation. So what we have is tau j, tau I plus 1, up to tau j minus 1. And then we have our two tau j's that we've added in because those are equal to the identity. Then we have sigma j minus 1, tau j minus 2. And so then here we want to use the mixed braid relation, which gives us so we'll have tau j minus 1, sigma j, tau j minus 1. And then here we have to use the tau braid relation. So now we'll have tau j minus 1, tau j, sigma j, tau j minus 1, tau I. And now this tau j, so next to it, what I haven't written is that it's tau j minus 1. Our commutivity of the tau braid relation will send it all the way to the end. So we'll have a tau j squared at the end, which is equal to the identity. So what we're left with is tau I plus 1, all the way up to tau j, sigma j, tau j minus 1, tau I, which is equal to sigma I j plus 1. And then to see that they're fixed, it's the exact same computation where either the tau j's just completely go through the entire thing because of far commutivity, or you end up using the same type of braid relation to pass it through, but it doesn't actually touch anything. So nothing will change. So what we see here is that we satisfy the conjugation relation, but we certainly don't satisfy the commutivity relation for the totally symmetric sets. So what we would hope is that there's some way to get these elements to commute so that we can have a totally symmetric set sitting inside of the pure virtual braid group. All right, so there is a way to do this, and it's called the overcrossings commute relation. So the overcrossings commute, which we call the OC relation for short, is defined as this mixed relation where you have the two sigma generators with the tau generator. So what this looks like is you have your tau, and then you have your sigma I plus 1 and your sigma I, and that's going to be equal to this. So what it's saying is that the bottom strand is able to travel below, like it's able to travel under the virtual crossing. And so a really interesting fact about this overcrossings commute relation is that it implies that you can have far commutivity so long as 3 of the indices are the same, not just that 2 of the indices are the same. But for all of the elements in our Ri set, any 2 of them will only have 3 different indices between them. So the OC relation, and this is a bit of a more algebraic proof, it's a little bit harder to see why the OC relation implies this. But so we can see that if we include the OC relation in our generating set, then we're able to let our I set be a totally symmetric set. So here comes, yep.
1 second, can you go to the next slide? 1 second. This OC relation and the relation which we have written above, the braid relation, kind of braid relation in the presentation, is how they are different. Like, look at the I, sigma ij, sigma ik, then they should also commute, no? In the presentation of the group. Presentation of the group, the second relation in the presentation of the group.
Yeah, so that braid relation isn't going to give you that they commute.
So in the presentation of the group, the second relation, take the first part, sigma ij, sigma ik. That
right,
is
but you
also,
have the sigma jk as well.
but sigma I and sigma ij and sigma ik will commute.
I do not believe that in the regular virtual braid group that they commute.
But OC relation says that. Huh?
The OC relation will, yes, but it's a bit of a longer computation, so I haven't prepared to present it. So
Neeraj,
if you include,
saying that from the OC relation it will follow that they will commute?
No. I'm not saying it's follow or something. I'm just asking that above also you have something written, something similar to these two relations. Is these two relations okay? Maybe need a more. Yeah.
The minute that you include the OC relation, then you're able to get the sigma ik and sigma ij commute. But before including it, those 2 elements certainly do not commute.
Okay.
I don't have a great reason for why they don't commute. It's kind of just all long algebra
okay.
expressions.
So after putting the OC relation, they will commute.
They will commute, yes.
In our welded virtual braid group, The OC relation is not true.
The OC relation is not true. No, there is no
Okay.
OC relation for virtual break groups.
That's okay.
Yeah. And so this is why we want to introduce welded braid groups, because in welded braid groups, you're allowed to have the OC relation.
Okay.
Yeah, sorry. I guess that these slides weren't in a great order.
So in virtual braid group, there is no totally symmetric set, or
Can you repeat the question, please, Samya?
in virtual braid group, do you have totally symmetric sets?
We haven't found any that are large enough. So we can find a couple of really small ones, but they're not really interesting enough. So because the braid group sits inside of the virtual braid group, those are the
Yeah.
best totally symmetric sets that we found so far. But we haven't found any interesting totally symmetric sets that aren't just the regular totally symmetric set we found in the braid group. And what we're really hoping to do is find an even bigger totally symmetric set because we have so many extra generators.
Right.
So that's our goal. So unfortunately, we haven't found any interesting totally symmetric sets that aren't just the totally symmetric set in the braid group, but you can find really interesting totally symmetric sets in welded braid groups by introducing this OC relation. But that's not to say that there aren't more interesting totally symmetric sets sitting inside the virtual braid group. It just means that we weren't creative enough to find them. Okay. So now I want to introduce the pure welded braid group. And what the pure welded braid group is it's the pure virtual braid group where you also include the OC relation. So now because we've included the OC relation, we have the set of sigma ij elements where you fix I and you let j be bigger than I be a totally symmetric set in the pure welded braid group. And we actually get more totally symmetric sets. So if you fix the element I and you let j be less than I, that's also a totally symmetric set for the exact same reasons. And interestingly enough, if you take the union of these two sets, so if you fix one of the if you fix the first component of sigma ij and you let j be every other index possible, you get that entire set is a totally symmetric set. So each of these totally symmetric sets are quite large. The size of them are always n-1. So before I'm going to talk about the work that Nancy and I did, where we bounded the finite quotients of virtual and welded braid groups, I think it's good to talk about homomorphisms between pure virtual braid groups and other groups. So a lot of this work was done by Bellingary and Paris, and they were able to classify automorphisms of virtual braid groups. They were able to classify homomorphisms from virtual braid groups to symmetric groups, and also homomorphisms from symmetric groups to virtual braid groups. So to get started, we need to define some epimorphisms from the virtual braid group to the symmetric group. So we're going to let the elements Si denote the transpositions of the symmetric group. So we'll let I go to I+1. And we're going to denote the epimorphism pi sub p from the virtual braid group to the symmetric group to be the elements where we send both the generators sigma I and the generator tau I to the equivalent transposition in the symmetric group. And so fun fact about this map is that the kernel of this map is actually the pure virtual braid group. And then we have a second epimorphism, which we denote as pi sub k. And for this epimorphism, you're going to let all the sigma I generators go to the identity, and we're only going to send the tau generators to the transpositions. And a fun fact about this is that you're actually able to show that the kernel of this map ends up being an Artin group, which is kind of neat, in my opinion. And so what Bellingary and Paris were able to show is that if you let n and m be natural numbers, where m is bigger than 5 and n is larger than m, then you're able to show what's the homomorphisms from a virtual braid group to a symmetric group end up looking like. And so up to conjugation, one of the following is going to hold. So you either have that the map V is abelian, or you have that M is equal to N, and you're equal to one of the two epimorphisms from the previous page. Or when M is equal to N is equal to 6. So in the case where both of them, so you have 6 strands, you end up getting a different answer, because there's this map from the symmetric group to the symmetric group that sends the transposition to these complicated elements. And so when you compose the epimorphisms with this nu sub 6, you're able to also find homomorphisms from the virtual braid group to the symmetric group. And so if we remember, S1 is just equal to the transposition 1, 2. And so we send the transposition 1, 2 to the permutation 1, 2, 3, 4, 5, 6. Then we're going to send the transposition 2, 3 to 2, 3, 1, 5, 4, 6. The transposition 3, 4 to 1, 3, 2, 4, 5, 6. The transposition 4, 5 to 1, 2, 3, 4, 4, 6. And the transposition 5, 6 to 2, 3, 1, 4, 5, 6. And so I don't expect you to remember this automorphism from the symmetric group to itself, but it does come up in all of the other classifications of the maps from virtual braid groups to symmetric groups. So again, if we let the generators of the symmetric group, so the transpositions, be denoted by SI, we're going to denote the map iota from the symmetric group to the virtual braid group, where we send the transposition I plus 1 to tau I. So then if we have a homomorphism from the symmetric group to the virtual braid group on M strands, then up to conjugation, one of the following will hold. We'll either have that phi is abelian, or we'll have that M is equal to N, and then phi is equal to iota. Or we'll again have that M is equal to N is equal to 6, and then you're going to compose nu sub 6 with iota. And now looking at automorphisms of the virtual braid group, we're going to have two different maps. So the first one, which we denote by zeta sub 1, we're going to take the element, the generator sigma I, and we're going to send it to sigma I conjugated by tau I. And then we'll just send tau I to itself. And the second map, zeta 2, we're going to send each sigma I to its inverse, and we'll send each tau I to itself. So a neat fact about these maps is that they actually commute, and they each have order 2. Seeing that they have order 2 is quite easy. So for the first map, when you send tau I to itself, that's trivially going to be order 2. But then when you send sigma I to tau I, sigma I, tau I, when you send tau I, sigma I, tau I back through the map, you're going to get tau I squared, sigma I, tau I squared, which is equal to sigma I. And then to see they commute, you just check that they end up commuting on the generators. And you see that sigma 1, sigma 2 of sigma I, this is just equal to sigma 1 of sigma I inverse, which is equal to tau I, sigma I inverse tau I. And similarly, zeta 2, zeta 1 of sigma I is equal to zeta 2 of tau I, sigma I, tau I. And then because it's a homomorphism, we'll end up getting tau I, sigma I inverse tau I. So these maps behave really well with each other. And that actually ends up showing that we can generate the subgroup of the automorphism group of VBN, which is going to be isomorphic to Z2 cross Z2. Okay, and so one of the last things the Bellingerian pairs did was they classified automorphisms from the virtual braid group to the virtual braid group on either the same number of strands or less. And up to conjugation, they found that one of the following holds. So you either have the phi is abelian, or you have that M is equal to N, And phi has to be either pi p composed with iota or pi k composed with iota. Or you have that m is equal to n is equal to 6, and then you have pi p composed with nu 6 composed with iota, or pi k composed with nu 6 composed with iota. And lastly, you can have m is equal to n, and then phi is going to be in the subgroup generated by zeta 1, zeta 2. Okay, so from the work of Bellingary and Paris, we're actually able to talk about whether virtual braid groups are Hopfian or co-Hopfian. And I also think it would be interesting to compare and contrast in the case of the braid group. So we say that a group is Hopfian if every surjective homomorphism from a group to itself is also injective. And a fact about the braid group is that the braid group is actually Hopfian. And so this follows from work by Bigelow and Kramer, who showed that the braid groups are linear. And it also follows from work of Malchev, because he showed that finitely generated linear groups are residually finite. And additionally, they showed that a finitely generated residually finite group is Hopfian. So since Bigelow and Kramer showed that they're linear, by Malchev, we know that they're residually finite. We also know from the presentation of the braid group that it's finitely generated. So Malchev was able to show that the braid group must be Hopfian. So from the work of Bellingary and Paris, they were able to show that the virtual braid group itself must also be Hopfian. And so the reason why this is true is because they were able to show that up to conjugation, the only surjective homomorphisms from the virtual braid group to itself have to be elements of the subgroup generated by zeta 1 and zeta 2. But zeta 1 and zeta 2 are automorphisms, so they're isomorphisms from the braid group back to itself. So this shows that the virtual braid group has to be Hopfian, because every surjective homomorphism is injective if they always have to be an automorphism. Right. So we say that a group is co-Hopfian if every injective homomorphism from a group to itself is also surjective. So this time we've just replaced injective and surjective. We've swapped the two terms. So the braid group is known to not be co-Hopfian. And an example of a map which shows that the braid group is in co-Hopfian is the following. So let Z generate the center of Bn. So if you remember what this is you're taking the disk and you're doing a full 360-degree turn. And you're going to let T be a fixed non-zero integer. So if you have a map that sends a half twist of a curve to the element where you do the center to some power times the half twist, this map will be injective, but it can't be surjective. So this shows that the braid group cannot be co-Hopfian. However, just because the braid group is in co-Hopfian, it doesn't mean that it's not almost co-Hopfian. And so what Bell and Margalit did is they did show that the braid group is almost co-Hopfian. And what they mean by almost in this case is that if you look at the braid group modulo its center, this will be co-Hopfian. So on the other hand, Bellingary and Paris were able to show that the braid group is co-Hopfian. And the proof for how the virtual braid group is co-Hopfian follows the same way that they were able to prove that the braid group is Hopfian by looking at the characterization that they had of maps from the virtual braid group to itself. They were able to show that injective homomorphisms must also be surjective. So this follows from their classification of automorphisms of the virtual braid group. Okay, so this is the work that's been done in the past. And now we can get to the work that Nancy and I have done recently for bounding finite quotients. So recall from the last talk that we have this really basic blueprint for bounding finite quotients. So we're going to let phi be a map from a group to another group. And we're specifically going to look at the welded braid group today. And using the welded braid group, we can also get some results for the virtual braid group. So in our case, we're going to let phi be a group homomorphism from the welded break group to any other group. And our goal is to find large totally symmetric sets in the welded break group. And we're going to bound the size of its finite quotients. So what we were able to find is the following. So we had to let the welded break group have at least 6 strands. And we let phi be a homomorphism from the welded break group to another finite group G. And then one of the following must be true. You either have that the map is abelian, or the map restricted to the pure welded break group is cyclic, or you have that the size of its image has to be bounded below by 2 to the power of n minus 2 times n minus 1 factorial. Or we have something a little more complicated. So we either have that each of those totally symmetric sets that include all of the sigma ij's where I is fixed, they have to map to a single element such that the image of those elements squared do not equal. And then we see that we have the same lower bound as we did for the braid group. And the reason for this is the most that we can do is we can factor through the braid group and use the totally symmetric sets from the braid group to bound the image. So a new tool that we developed to help us study the finite quotients of welded braid groups is something that we call the hot air balloon lemma. And we called it the hot air balloon lemma because we thought that it would look really cute sitting inside of a hot air balloon, because you can see each of the elements and they have to map down to a new element in the image. And so what the hot air balloon lemma says is, so we have our collection of totally symmetric sets where you end up fixing the first index, but you range over the second. So A1 is just sigma 1j, where j is bigger than 1. And then AN is sigma nj, where j is less than n. And we're going to take some subset of this collection of totally symmetric sets in the welded braid group. Then if we let phi be any non-abelian group homomorphism, and phi does not split any of these totally symmetric sets, and we have that the image of each of these totally symmetric sets squared, because remember, by the lemma by Margalit and Kordek, you have the phi of AI. The size of it is either equal to 1, so some one group element, or it's equal to the size of the totally symmetric set. So here, this is just one group element. So if each of the elements squared are distinct in the image, then you can build a totally symmetric set out of these group elements. And so the proof structure to prove that the hot air balloon lemma holds is similar to any other of the proofs that we've done to prove that a set is totally symmetric. There's just a couple of extra things to check because you're mapping something into the image. Okay, so what we need to know now is what are all the totally symmetric sets in the welded braid group? So on the very left, we see that we have the totally symmetric sets where you fix the first index, and then you're looking at all the indices that are less than it. So here we have sigma 2, 1, and then at the bottom we have sigma n1, sigma n2, all the way up to sigma n minus 1. But something interesting to note is that when you take the inverses, you end up getting sets here that satisfy the conjugation condition. But not the commutivity condition. But something that we noted the last time is that you only need the conjugation condition to determine whether or not a set splits. So if you have the conjugation relation, then we can talk about whether or not the map splits the set or not. Because then we have that the size of the map of Bi is either equal to 1 or it's equal to the size of the set. So even though they're not totally symmetric sets, they can still be really useful for us. And so then in the middle, we see that we have the sets where you fix one of the indices, but the second index ranges over all of the other values. And then on the very right, we have the set Ri, which we showed was totally symmetric earlier on in the talk. And again, we see that we have these inverses. So all of the sets here satisfy the conjugation condition, but they do not satisfy the commutivity condition. So again, here's the statement of the theorem that Nancy and I showed. And what we want to do is use the totally symmetric sets on the previous page to show that you have a large number of elements which need to split in the image. Namely, that one of the bigger totally symmetric sets that we have has to split in the image. So I'm going to do a sketch of our proof. And the first thing that we're going to assume is that our homomorphism won't be abelian, and it's not going to be restricted to, and the restriction to the pure welded braid group won't be cyclic. We're not able to say much more about these two conditions. And so because they're two statements in the theorem, there isn't much to show here. So we're just going to suppose that we're in neither of these cases. And so our first case, so now we're going to figure out whether or not we're going to split any of the AI totally symmetric sets. And the first case is that we do split one of these AI totally symmetric sets. So remember these totally symmetric sets, something that Chudnovsky, Kordecki, and Parton showed is that if you have a totally symmetric subset of a group of size n, then you have that the group itself that contains this totally symmetric set, the size of it has to be bounded below by 2 to the power of n minus 1 times n factorial. So since we split one of these AIs, and it's a totally symmetric set of size n minus 1, we apply this lemma by Chudnovsky, Kordecki, and Parton to show that the image of the welded braid group is going to be bounded below by at least 2 to the power of n minus 2 times n minus 1 factorial.
Excuse me?
Yeah.
Can you go? The last the theorem you stated, in the last talk, we have improved this result now, where this 2 can be replaced by 3.
Yeah.
So why not we are applying that here, because we get a more.
So you can replace the 2 by a 3 for the case of the braid group. So I don't think it was shown that you can replace the 2 by a 3 for any group, just for the braid group. Because in the braid group, you always, pardon?
That is only for braid groups.
I believe that it was only shown for braid groups. I don't think anybody has shown it for groups in general, because what you need to get the 3 is that each of the elements in the image, that their squares are never equal.
Okay.
And I don't know if it's true in the case of the welded braid group that if you map each of these elements into the image, that the squares of the generators can never equal each other. So that's something that's true for the braid group, but I do not know if it holds for virtual braid groups or welded braid groups or groups in general. So it's true that Kaplinger and Kordecki did prove that you can replace the 2 by 3 in the case of the braid group. I do not know if it's true in general. Okay, so now we've done the first case. And so our second case is going to be that phi does not split any of the totally symmetric sets AI. And so we're going to denote the image of each of these AIs by GI, because remember, if it doesn't split, it just maps to one element in the image, and we're just going to denote that element by GI. And what we're going to do is we're going to further suppose that there exist indices so that the elements squared do not equal each other. And so a lemma that's true about virtual braid groups is that if you have a homomorphism from a virtual braid group to any group, which is a group homomorphism, so that either the map restricted to the symmetric group or the braid group is abelian, then the map itself must be abelian. But we're assuming that the maps are not abelian. And so by the above lemma, we're allowed to suppose that the map phi sends the tau I generator not to the identity, because we're not going to be cyclic on sigma n. And so what our goal is going to do, our goal is going to be to consider all the different cases on I naught and J naught. And what we want to do is get to a point where we can apply the hot air balloon lemma. Because if we can apply the hot air balloon lemma, we can get really big bounds on how big the image is going to be. So the first subcase of case 2 is we're going to suppose that both I naught and J naught are less than n. And because all of the other cases are similar, we'll just focus on this case. And then if you're interested, the other cases are in our paper, but they're approximately the same. But since we're looking at the case where I naught and J naught are less than n, we're going to look at the subset of totally symmetric sets that we denoted by Ri. And what we're going to do is show that one of the large Ri's has to split. So we know that Gi naught squared cannot equal J naught squared. And this means that you have to have that, this also implies that Gi naught does not equal Gj naught. So then we have two elements in our totally symmetric sets that are not going to be equal to each other. And then notice that if you take their inverses, they live in the bottom row, which satisfies the conjugation condition. And because the bottom row satisfies the conjugation relation, this bottom row here has to split. So this means that Gin inverse does not equal the image of sigma Jn inverse, which means that each of these rows has to map to a different element. And so by the conjugation relation, if there exists a P so that Si to the power of P is equal to Sj to the power of P, then every single element, Si to the P, has to be equal to Sj to the P. But from above, we have that two of them are not equal to each other. So that means that the squares of every single one of the elements that R1, R2, all of these Ri's map to, they are not able to be equal. So what we have is that each of the Gi squareds are unique. And so what we're able to do is apply the hot air balloon lemma. So now we're able to use the bound that the hot air balloon lemma gives us for the size of the image of the welded braid group. So sorry, I did not write down the bound for some reason, but this bound ends up being, once again, you'll get that phi of WBN is going to be bounded above by 2 to the n minus 1 times n minus 1 factorial by the hot air balloon lemma. And so the further subcases in case 2 end up being the same type of argument as this case here. And so we have one last case left. We have the case where phi does not split any of the AIs, so any of those totally symmetric sets, and there does exist a phi of AI squared, which equals phi of AJ squared for all I and J. And so at this point, the best that we're able to do is use the fact that phi restricted to the braid group is not cyclic. So then at this point, we're able to apply what we know about the braid group from last time, because a totally symmetric set of the braid group is also a totally symmetric set of the welded braid group, because the braid group is a subgroup of the welded braid group. And so we're able to apply the bounds that we found last time to the case of the braid group. So we have the bound the floor of n over 2 plus 1 times 3 to the power of the floor of n over 2 minus 1 times the ceiling of n over 2 factorial. Oh, sorry. And so we apply this above theorem to our homomorphism, which is restricted to the braid group. And so this ends up giving us the theorem that we just showed. You either have that our map is abelian, the map restricted to the pure welded braid group is cyclic, or you have that the image is bounded below by 2 to the n over 2 to the n minus 2 times n minus 1 factorial, or you end up having that every single ij, every single ai has to map to a single element, that these elements squared at some point do not equal themselves, and then you're bounded below by this value. And so what about the virtual braid group? Well, the virtual braid group is a quotient of the welded braid group. So we're able to use what we know about the welded braid group to say some things about the virtual braid group. So for the virtual braid group, we have to consider at least 6 strands. And so we have a map from the virtual braid group to any finite group G. And then we know that one of the following must be true. We either have that phi is abelian, or we'll have that the map factors through the welded braid group, and either the map restricted to the pure welded braid group is cyclic, or we'll have that the image of the map is going to be bounded below by 2 to the power of n minus 2 times n minus 1 factorial. Or we have the case that for all I and j, phi does not split ai, and the images of the elements squared will not equal each other. So then we're able to bound it below by the floor of n over 2 plus 1 times 3 to the n minus 2 times n minus 1 times the ceiling of n over 2 factorial. And this purely follows from the welded braid group theorem. Because we're factoring through the welded braid group, we're able to use the totally symmetric set sitting inside the welded braid group and give bounds that way. Similarly, if we do not factor through the welded braid group, we know that the braid group is a subgroup sitting inside of the virtual braid group. So we're able to bound the size of the image of the welded braid group by the bound that we found last time for the braid group itself. And so this gives an overview of the work that Nancy and I did, as well as ideas of how we proved our theorems. And this is what I have prepared for you guys today. So thank you so much for listening.
Yeah, thanks, Yvon, for the nice overview. Any questions? So you said that as WBN is a quotient of VBN, I mean, using whatever you have done in WBN, you have similar statements for VBN also, right?
Yeah.
So
because
okay.
it's purely because when you take the virtual braid group and you mod out by the OC relation, you're able to find maps that way. So whether it factors through the welded braid group or not.
So from WBN to VBN, you have inclusions, some kind of inclusion map through which you are seeing the totally symmetric sets in WBN inside a totally symmetric set in VBN.
Yes.
I see.
Yeah. So you're just utilizing that map. It's not particularly enlightening. It would be a lot more interesting if we could find interesting totally symmetric sets sitting inside the virtual braid group, but we were only able to find something interesting sitting inside the welded braid group. So we're restricted by the map that sees this quotient.
Yeah. Any other questions? Oh, let me ask another question then. So So apart from these braid groups and generalizations of braid groups, what are the other groups where some examples of totally symmetric sets have been found so far?
So like all mapping class groups have totally symmetric sets. So if you look at a multi-curve, so multi-curves are defined to be curves that are disjoint. Any large collection of curves that are all disjoint from themselves is a totally symmetric set. Because if you look at the mapping class group, any two, so I guess I should say multi-curves so that each of the curves are non-separating. Because of the, I'm forgetting, change of coordinates principle, any non-separating curve, there exists a homeomorphism that maps that curve to another curve. So to another non-separating curve. And so you're able to see that mapping class groups also contain large totally symmetric sets. And I believe that these large totally symmetric sets were utilized in work by Lei Chen and I'm constantly blanking on that last name, but they ended up using the large totally symmetric sets sitting inside mapping class groups to classify maps from the braid group to mapping class groups of surfaces, so surfaces of genus G. And so the work by Aramayona and Soto, where they show homomorphisms between mapping class groups, are able to recover that using only totally symmetric sets.
Yeah, I see.
Yeah, I don't know. And then the work of, I think it was.
But what about arting groups, Coxeter groups? Do we have examples of totally symmetric sets there?
Yep. A lot of Coxeter groups and Artin groups have braid groups sitting inside of them. So those are some trivial totally symmetric sets that are sitting there. And Nancy Sherrick, Thomas Ning, and myself have been looking for larger totally symmetric sets living inside of Artin groups to see if we can utilize anything about totally symmetric sets to say anything about the classification of Artin groups. So we're trying to do something similar to classify homomorphisms from Artin groups to different Artin groups, usually utilizing these totally symmetric sets. So yeah, inside Artin groups, there's also fairly large totally symmetric sets. And then Lee and Parton have done classifications of totally symmetric sets sitting inside of dihedral groups, free products of groups. They've done quite a few different groups. I can't remember all of them off the top of my head.
Okay, thanks a lot, Yvon, for the very nice and informative talks on your work. Yeah, thanks a lot.
Yes, thank you so much for having me.
Yeah.
Shomuda, just can you stay for a minute?
Yeah, sure.